Okay, welcome back everyone to the undergraduate seminar. I'm very excited to have David Schrittesser here, who's going to tell us about infinitesimals. So thank you very much for coming out. Thank you for preparing this talk. I want to say this was the most surprising offer to speak at the seminar we've ever received. David got in touch with me this weekend and said, could I please speak next week? I'm offering this course. It's going to be amazing. We have to talk about it. So I'm very, very excited to hear what you have to say today, David. Thank you for coming out.
Thank you. Thank you for having me. Yeah, I mean, I hope it works out. It's a bit of an experiment because although infinitesimals will make your life better, as the talk of my title suggests, it's not entirely easy, to give a quick introduction to them. So yeah, but I did my best, and we'll be talking about it for a whole semester, hopefully next semester. It's not entirely clear yet if that course will actually happen, but it probably will. So yeah, okay, I misspelled my name. Schrittesser is spelled with 2T, but yeah, I mean, maybe one of the T's is infinitesimal. All right, so let's start. Let's jump right into it. What are infinitesimals? Okay, first of all, I also want to say, please interrupt me at any point, and talk to me, make comments, ask questions. There is nothing, there's nothing too stupid, or I mean, there is actually nothing stupid. Just say whatever comes to your mind if you can. All right, so infinitesimals. Let's first of all find out what are infinitesimals. So let's just take some ordered field that we call star of R, because it's not the normal reals, and it's got some operations on it, which are not the ordinary field operations. It's just some ordered field, but we want the ordinary reals to be a subfield of it. And because the plus and the times and the less than of this bigger field extends the operations on R, we just drop the stars from plus, times, and less than most of the time, almost, actually always, pretty much always. But they're operations on this bigger space. So an element of these star reals, they're actually called the hyperreals, is called if an infinitesimal if and only if it's between -1 over n and 1 over n for every natural number n. Right? Smaller than 1 over n. So my first question to you is, are there any infinitesimals in the ordinary reals?
Yeah, 0.
Yeah, 0, exactly. Yes. Yeah, but in our star, there might be other ones, right? It could be that there's more infinitesimals than just 0. So, so suppose you've got some delta, which is infinitesimal, but it's also larger than 0. Here I wrote the star for the larger than, just to remind you that it's some weird relation, but I will stop writing the stars on the relation, on these basic relations. So if you look over at 1 over delta, then of course it's going to be bigger than every natural number. And an element capital T, capital D in these hyperreals with this property is of course called infinite. So once you've got infinitesimals, you've also got infinite numbers. That's pretty clear. Basic exercise. So now let's suppose that, I mean, could be that star R is just the reals, but that would be pretty boring. So let's suppose that the hyperreals contain a positive infinitesimal or a non-zero infinitesimal, some non-trivial infinitesimal. Then one usually introduces this equivalence relation to hyperreals are called approximately equal if they're infinitesimally close to each other. So that introduces an equivalence relation, and its classes are called monads. I guess following Leibniz. And a hyperreal is called near standard if it's approximately equal to some of the normal reals. So if it has a normal real in its monad. By normal, I mean ordinary, an ordinary real, an element of R. And for such a near standard real, we can talk about the standard part of X, and that's just the unique standard real element of R, which is infinitesimally close to it. All right, so why is it unique? Why is this R unique?
Since for any other real, we can difference from R, there are, we can find the one interval of length 1 over n between the two.
Yeah.
Between this real and
yes,
R.
That's true, yes. Or another way you could say it is, well, if there's two reals which are infinitesimally close to X, they'd be in the same monad, so their difference would be an infinitesimal, and the only, and it would be in R because the difference of two standard reals is in standard reals. So the only infinitesimal in R is 0. So their difference has to be 0. But that's exactly the same argument, just actually yours is maybe prettier. Mine is longer. Less to the point, maybe. So, okay. So why is it unique? I already asked you that. So are the infinitesimals or the near standard numbers a field? Question to the audience. First of all, are the infinitesimals, if you just look at the infinitesimal elements of star R, do you get a field? Is it a subfield of R? Well, remember what we did on the last slide here. If we've got an infinitesimal and we take 1 over it, it's not infinitesimal anymore, right? It's infinite. So the infinite numbers are not infinitesimal. Okay, so the infinitesimals don't form a subfield because it's not closed under taking inverses. Is that clear? Okay, and the near standard numbers are not a field for the same reason, right? Because if you take the near standard numbers contain the infinitesimals, and if you take the inverse of a near standard number, you get an infinite number, and an infinite number isn't near standard. No, so the answer is no. But the infinitesimals as well as the near standard reals form a subring of the hyperreals. So if you take any near standard real and you multiply it by a standard real, you get a near standard real. And if you take a standard real and you multiply it by an infinitesimal, you get an infinitesimal. So actually they're an ideal. The infinitesimals are an ideal in the near standard reals. If you multiply a near standard real by an infinitesimal, you get an infinitesimal. So what if you take an infinite real and an infinitesimal real and you multiply them together? Do you get something infinitesimal? Do you get something near standard? Or do you get something infinite? Or maybe you can't tell. Maybe this isn't the same always. What do you think? Take a wild guess. No one? Come on.
Oh, sorry, the chat's going crazy.
Oh, it's in the chat. People do it in the, okay. Let's just, where is the chat? Yeah, maybe not always the same. Yes, that's the right answer. Yep. So, I mean, we haven't said much about these hyperreals right now, right? So we really don't know much about how they how they will act. And so here's a picture of the hyperreals. You've got the ordinary reals sitting in the middle. Well, I mean, if you've got the ordinary reals, if you don't look too closely, right? But around each of these ordinary reals will be a monad. So that's what's in these bubbles. A monad of reals infinitesimally close to it, to the standard real. So this middle part here, together with all the monads, is the near standard reals. So all the standard reals or the reals that are infinitesimally close to a standard real. And then on the outside, there's going to be positive infinite and negative infinite reals. And of course, they also have infinitesimals close to them. They also have a monad close to them, each one of them. All right? Okay. Oh no. Okay, so recall that the reals are what is other, it just should say is the, recall that the ordinary reals are the unique Dedekind complete ordered field, right? That's how they are defined. So what about the hyperreals? Are they going to be complete? Oh, what does the monad of an infinity look like? That's a really good question. Let me see. What does it look like? Well, I mean, you know, if you divide by an infinite number, it's by a large enough infinite number, it's going to look like a monad of 0, right? I guess that's one thing you can say about it. So, you know, these things, it's a field, so you can scale and you can translate, and that makes it very, very self-similar. There's a lot of self-similarity, but actually what these monads really, really look like depends a lot on your particular model of the hyperreals. There's more than one. So yeah, a very simple one, actually, maybe the smallest one. If you look at the monad of 0, it looks like this. You take a copy of the rational numbers and you replace every rational by a copy of the integers. So just, you know, just thinking about the order structure of that will give you a good idea of what the monad of 0 looks like. But that's only in a very simple hyperreal field, and there's different hyperreal fields. So in any case, so my question still stands: is it a complete field, the hyperreals? Can the hyperreals be a Dedekind complete ordered field? Oh, what is a complete field? Oh my God. A complete field is one where you can take the supremum of any set. Every Dedekind cut has a separating number, or if you could also say every Cauchy sequence converges inside the field. So yeah, exactly. And the answer is correct. The answer that Parker gave, they can't be Dedekind complete because the only Dedekind complete ordered field is R. So this one is the hyperreals are incomplete. No, I think Dedekind completeness and Cauchy completeness are the same in an ordered field. They might differ on some weird space. I don't know what it takes for them to differ. Maybe they can they differ on metric spaces? Probably not. Yeah, I mean, but for an ordered field, well, at least in a Dedekind complete ordered field is also Cauchy complete, and vice versa, I guess. Yeah, the topological vector space definition of Cauchy is not in a field. So yeah, in a topological vector space, I suppose they're not the same, but my brain doesn't really work.
Well, usually when you have
very well
Cauchy,
with
you
that.
have like a metric space, right?
Yeah.
You're talking about the distances.
Yeah, if you have Cauchy, you need a uniformity, right? I mean, I'm not really very good at hopping around like that. So if I say something really stupid now, that might very well be. So I preparing this talk, I haven't really thought about the difference between, but for reals, there is some reason why in the context of the real numbers, it doesn't matter why you talk about Cauchy's complete or Dedekind complete, and I can't really recall it now. I'm sorry. But in any case, as Parker said, the hyperreals can't be complete because otherwise they'd just be the reals and they wouldn't have any infinitesimals other than 0. And here's maybe a more informative way to see it. So look at the following number if it exists. Suppose you've got an S which is equal to the supremum of all the near standard reals. So it would actually be the same as the supremum of the ordinary natural numbers. Now, this can't be, this S can't exist in the hyperreals because it would have a predecessor, right? S minus 1. And it's easy to see that S minus 1 would actually have to be near standard. And it would also have to be greater than 0. I mean, if S minus 1 is less than 0, then S would have to be less than 1. So S certainly can't be the supremum of all the near standard real numbers. So yeah, so S minus 1 would have to be near standard, but the near standard reals are closed under addition. So S would also have to be near standard. All right, so the hyperreals have to have holes. And the reason they have to have holes is because they fall apart into this near standard and infinite part. There can't be a number separating these two.
Sorry,
You have nowhere to put it.
Isn't this subset should has an upper bound to speak about the soup?
It does have an upper bound, but it doesn't have a least upper bound. And that's exactly the reason why it's not complete. I mean, completeness means that every bounded set has a least upper bound. So there's no holes in the order structure. Does that make sense?
So an upper bound would be any infinite hyperreal, right?
Yes, exactly. Very good. Yes. Any infinite hyperreal would be an upper bound. But another way to say it is there's no smallest infinite hyperreal. And that's actually, again, that's a much better way to see it. If you'd have a smallest infinite hyperreal, you take -1 of this real and it would still be an infinite hyperreal. So it wasn't the smallest.
Does that type of argument also apply to, like, let's say if you had the set of near standard, I guess the set of near standard infinitesimals to 1, if that makes sense?
The monad of 1, yeah, that's called the monad of 1. Everything that's infinitesimally close to 1, you mean, right?
Yeah.
Yeah. Mm-hmm.
So what if you took, would that have no supremum?
Exactly, that would also have no supremum for the exact same reason, yes. Yeah, so R gets split up into this mass of similar looking, I don't know, monads. The big ones are called galaxies, but it's very, very self-similar somehow. And the idea is really, so the way I would like to see it is that working with the hyperreals helps us to differentiate vastly different scales, right? And that's something that the actual real numbers are not very good at doing, right? I can't say, it's very hard to say, I won't care about anything that's bigger than 10 million, because the way math works, you can always go from 10 million to 10 million plus 1 by just adding 1, right? And so math, the ordinary reals are really bad when you want to talk about vastly different scales. And the hyperreals give you a way of talking about vastly different scales. You could say, my monad is everything that's here on Earth. and the actual reals, they would describe, you know, things that happen on Jupiter or something like that. And for all practical purposes, I will never get from Earth to Jupiter. And the hyperreals are a better model for that than the normal reals that we work with. All right. Okay, yes, so the near standard reals are closed under plus, I said that. Or I say here, you can also use that a complete field must be Archimedean, a complete ordered field must be Archimedean. But yeah, that's just an aside. Let's not get into that. It's really only fun if you already know what Archimedean is. All right. Okay, so how did we get here and where do we go from here? So far, we have simply assumed that we've got a field extension of the reals called star R. We call it the hyperreals. And we've assumed that it contains at least one positive infinitesimal. And that's not a lot of assumptions. So does that help us to talk about, for example, convergence using infinitesimals? There's not really any indication so far of how to do that. Can we define derivatives using infinitesimals? Again, you know, just by assuming that infinitesimals exist, I don't think there's much hope of doing that. I haven't even argued that such a field extension even exists. Maybe such a thing doesn't even exist. I should at least provide some sort of argument that we can work with such a set of hyperreals. For example, can we present one such field extension with infinitesimals more concretely, like we did with R? When we learn about R, at some point we learn how to construct it as the set of Dedekind cuts in the rational numbers, and you somehow construct the real numbers from an object that you already understand, or you think you already understand. Something that you think that somehow feels easier, right? So can we somehow more concretely give an example of such a set of hyperreals? And well, all of these questions really have the same answer or the same answers. There's several options for how you could proceed. One is to just write down axioms for the hyperreals, and you just start working, and you don't worry about whether they exist or what they look like concretely. And every time you want to have a new property in your hyperreals, like that infinitesimals exist, you write down a new axiom and you hope for the best. I mean, of course, that's not the best way to do it, but I guess that's historically how people used to do calculus in some sense. Another way you could do it is you could use the completeness theorem from logic, and you could produce a structure satisfying such an axiom system using the completeness theorem. But I mean, I'm not assuming that you know what the completeness theorem is. I'm just mentioning this as an aside, because if you pick up a book about non-standard analysis, some books will do it like this. And the original way, the first way that it was ever done, and what I will try to do now, is you construct a model of the hyperreals, like you construct such a field extension very concretely, and you can do that by taking what's called an alter power of the reals. Okay, so here's a short intermission regarding the first of these possibilities. Just axiomatize stuff and work with hyperreals. Now, arguably, that's what Leibniz did. So here is the first page of Leibniz's new method, where it all started. This is where calculus started. And I know you can't read it very well, but read the first line. It's in Latin. He says something about ax, and there is something he calls curvae plurus, so that's several curves. And he calls them VV, WW, YY, ZZ. And then he goes on and on and on. But if you look down there, you see something like DZ minus Y plus W plus X. So you can see things resembling maybe something more modern than this VVWWYY. What the hell is that even about? But DZ looks a little bit more familiar. And I've looked up the English translation of this first page, and just sort of, I don't know, out of curiosity and for fun. This is not really very deep. I will present it to you very quickly. So what Leibniz says here in Latin is, let AX be the axis and several curves, he gives some name to them, but let's ignore that, of which the ordinates normal to the axis shall be Vx, which may be called respectively V and W and Y, whatever. And the abscissa for the axis AX may be called X. What the hell is he talking about? Okay, I parsed this for 10 minutes and I realized that the modern translation of this is, suppose V equals V of X. V is just what we would call Y. V is a real function of X. That's what he's trying to say here. AX, when he talks about AX, he just means that's the x-axis. Yeah, I'm also glad that we have more notation. This is just poor Leibniz. But yeah, he had to invent all of this, I guess. I mean, and also I guess this is their notation, right? People were used to this kind of lingo. Let AX be the axis and the ordinates normal to the axis, blah, blah, blah. I guess that was their conventions. And if you think about it, V equals V of X is also just a convention, right? Okay, now Leibniz goes on and he says, now some straight line taken arbitrarily may be called dx. Here we go. It's an infinitesimal, really. But he's not saying it. He's just saying, call it dx. Call something dx. And the straight line which shall be 2dx as v may be called dv, or the differentials of v. Now, I have no idea what this means, and actually no one had any idea what this means, and people complain about it. But, you know, interpreted it as Leibniz just saying dv is also something, and now he gives axioms for the relationship between dx and dv. And now he says, okay, we put in place the rules of calculation are as follows. With these put in place, with this notation, the rules of calculation are as follows. And now you will start to recognize something that looks very modern. He says, let A be a given constant quantity, then dA will just be 0. So the differential of A is just 0. And d of A of x will be equal to A times d of x. You've also seen that, right? This is just calculus. Then he says, if y is equal to v, so what he means is if v is the identity function, then dy will be equal to dv. Okay. And I guess what he means is that the identity function has derivative 1. And then he says, now for addition and subtraction, and then you get all the usual rules of calculus. And he's not, he's just stating these things as axioms. And then people calculated with those for hundreds of years. And Leibniz tries to help us with this table. I have no idea how this is going to help anyone. But actually, so the vertical line here is the x-axis, interestingly. And then, the curved things are some of these curves. So for him, the y-axis is in the horizontal. But weirdly, look at where dx is. dx, for some reason, is also in the horizontal. And I think that's just incredibly confusing. And maybe the printer made a mistake. So I'm really surprised that, people learned how to do calculus from this. But they probably just sat down and thought about this for a very long time. So this is the end of the intermission about Leibniz. Okay, so now I will try to tell you what an ultra power is. Let's see, what time is it? Okay, going well. What, there's a question. So do we just say monad because Leibniz did? The word seems a bit more loaded in math nowadays, but assume it has no correlation. Really good point. I was going to point that out and I completely forgot. Now, if you've ever programmed Haskell, or if you've ever studied category theory, then you know monad from an entirely different context, from an algebraic context, and it has nothing to do whatsoever with this use of it. So the other use is more or less oriented, it should sound like monoid, and it has nothing to do with the way Leibniz used this. But this calling the monads in this context is a nod to Leibniz, because Leibniz called them that. And let me say that this approach to analysis that I'm presenting now, it dates from the 1960s. It was invented by a guy named Abraham Robinson, and I guess he called these things monads, you know, as a nod to Leibniz. All right, so I hope that answers this question. No, it does not have a correlation. Oh, and then there's monadic second order logic. Oh my God, yeah. And I'm not really even, I don't even really know what monadic second order logic means. It just means what it has. Yeah, I don't know. This is not, so there's a lot of things called monadic. This is just one of them. It has nothing to do with monadic second order logic either. All right, so let's talk about ultra products. We want to find a model for the hyperreals. Let's start, you know, we want to make room for some new reals, right? So if you want to make room for new stuff, you know, you got to space out the things that you have, that you already have. Let's make some room to maneuver and take a product of R. By a product, I mean R to the n, that's an infinite product. That's just the set of functions from the natural numbers into R. And then if you've got a product, you know, you could hit upon just defining operations on this product component-wise, right? So your elements are now sequences. Let's just say we add two sequences by taking, you know, the sequence where we add the components of the old sequences, right? I mean, the sequence R bar plus R bar prime is defined by saying its value at n is what you get when you add the nth element of R bar and the nth element of R bar prime. It's just like in a vector space, it's component-wise addition. And we could also multiply component-wise. Although, you know, I mean, you know from vector spaces that this is usually not a good idea. It's dangerous. And that's actually why we will go to the ultra product in a moment, not just to the product. Okay, but let's just, you know, let's try this. Let's try this out. So this gives us two abelian monoid structures. That is very fancy lingo. It just means that plus and times are now associative and they're abelian. And you actually also have a neutral element for either of these operations, namely, oh, and they're even linked by a distributive law, these two things. It just all gets inherited from the normal reals because of the product-wise definition. And, you know, it's an exercise to check all these things. It's very easy. And the two neutral elements in this product, in this weird monoid, they're the constant function, the constant sequence with value 0 and the constant sequence with value 1. You know, if constant value 0, if you add that to a sequence according to these rules, you obviously get back the original sequence. So this is a neutral element. Okay, but you know what happens when you try to multiply vectors like that, right? If you look at the following sequence, which you know, R star of n is 0 when n is even, and it's just n or something else when n is odd. No, you've got infinitely many zeros and infinitely many non-zero values in your sequence. This can't. So what's wrong with that? You tell me. You tell me. What does anyone have an idea? What is an obvious problem with this thing? Well, what if you try to take its inverse with respect to multiplication? What's going to happen?
I'm just taking a wild guess here. I guess maybe you have some degeneracies with the multiplication there. If it's
Yeah.
a dot
Yeah.
product here, then you can have degeneracies, right?
Yes, exactly. Yes. So one, yeah. And then in the chat, someone said the even entries are non-invertible, and that's also true. Yes. So this whole thing in this monoid together with, the product-wise times and the unit, which is the constant function 1, this can have a multiplicative inverse, right? And what the other person, I'm sorry I didn't catch your name, said was also true. Like if you take the other real, which is 0 at the odd places, and you multiply the two together, you will get 0. So you get two non-zero elements, you multiply them together, you get 0. So there's your degeneracy. This is very far away from a field. We were not getting a field extension like that. And we're also not getting an ordered field extension like that. I mean, anything with a nice ordering on it. But let's try anyway. Let's say we could think of defining the order, a strict order on this product in the same silly way, just as the product order. This is called the product order. You just say one sequence is below the other one if and only if it's below the other one on all of its coordinates. And so how is that going to behave different from what we want in a completely ordered field? Any ideas? What will fail that we really want in our hyperreals to hold? Or how is this ugly? I mean, how is this not a nice definition? Yeah,
Trichotomy?
exactly. Pardon, what? Sorry, say it again.
Trichotomy?
Yeah, exactly. The trichotomy is going to fail. Yes, and someone is saying it in the chat as well. Yes, exactly. That's true. And there will be many, many incomparable elements. Anything where the order changes from one, how do you call this, component of the sequence to the one element of the sequence to the next. Okay, so but here's the way out. And this is what the people realized who invented this ultra power construction, I suppose. Perhaps we should temporarily consider the set of n where bar r is less than bar r prime of n, the set of coordinates where the relation that we want to hold does hold. Perhaps we should consider that as a kind of truth value for the formula bar r is less than bar r prime. And the same holds with this other example. Maybe if we want to ask if some sequence is equal to 0, the constant 0 function, maybe we should take the set of natural numbers where the component is 0 as a kind of truth value for the statement bar r equals the constant 0 function. So instead of just having true or false statements, now each statement has this generalized truth value, which is a set of natural numbers. Very weird, fuzzy notion of truth. And maybe from here we can get to the ordinary, to a good notion of truth. So we could try to find a map from the power set of the natural numbers. So the map takes as an input one of these truth values and transforms it to just 0 or 1. And we could try to find a map such that it helps us decide what is going to be true in our hyperreals. Or to put it in slightly different terms that are more common, let's look at the set at the pre-image of 1. So all the sets, that's all the truth values, all the sets of all the sets of natural numbers taken as truth values that we consider as true, as the truth value true, that we identify to true. This set we call U. Okay, this is going to be, later on we're going to take an ultra filter. That's why it's called U. So let's say U is the set of true truth values. And then we could define, we could just say that we want bar r to be less than bar r prime if and only if the set of natural numbers where this holds for the components is a true truth value. If we consider this one of the true truth values.
So if I'm understanding this correctly here, this map that we're looking for is kind of just encodes what we care about like in regards to certain sets that or certain I guess
Yeah.
functions that overtake each other in certain places?
Exactly. Yes,
Okay.
exactly. So yeah, but I mean, the thing is, how shall I put it? I mean, you will see how, yeah, but you will see. I will come back to your question when I've said more, but this is exactly the right intuition.
Okay.
Yeah, okay. So the point is that actually this is kind of also kind of an answer to your question. For this to make any sense though, this set view must satisfy some requirements. I mean, maybe this is what you were getting at a little bit, right? If you just take any old set U, you know, this won't help you. You still won't have trichotomy, and you know, you must choose a set U with very nice properties. For example, we will want to identify some sequences, right? Like we want to identify some of these degenerate elements with 0, right? So, and the way we just said we would identify them is we call two things equal if they agree on a set in U. I mean, if the set of coordinates where they're equal gets assigned truth value 1, right? And this relation should be an equivalence relation, right? Because we want this to be equality in our set of hyperreals. And from this being an equivalence relation, you very quickly see that you want your set U to be closed under intersections. Can anyone see why?
Because then the intersections would have to map to the same truth value, right?
Yes, exactly. Everything in U maps to 1, and we'll just map everything outside of U to 0. So if you want R to be equivalent to R prime and R prime equivalent to R double prime, then both of these equivalences are going to be witnessed by some set being in U, right? But you've got two different sets, one witnessing the first equivalence and one witnessing the second equivalence. And now you want the set, you know, where R of n is equal to R double prime of n also to be in U, so that this equivalence relation will be transitive. And for this, you want the two sets, you just take their intersection, right? That would be a good set to witness the equivalence you're looking for, and you want the intersection also to be in U. So this will indeed be an equivalence relation if U is closed under intersections. Does that make sense, at least intuitively?
One part doesn't make sense to me. So if you take the intersection of the sets like where like
Yeah.
R bar and R bar prime agree, and the set where R bar prime and R bar double prime agree, and you intersect those, then you get the set where all three of them agree, right? But then that might not be equal to this set where like we're just R bar and R bar double prime agree.
Yeah, that's a really good point, but it will be a subset. So actually I made a mistake here. So, and that's actually another thing we just want to be true about U. We want it to be closed under taking supersets. And that will solve the problem that you just mentioned. So actually, you're right. I should have said here, if this is to be an equivalence relation, we probably want U to be closed under intersections and taking supersets. Although I'm not entirely sure. Is that true?
It sounds like we're
Yeah,
talking
that's true.
about a filter.
Yes. Yeah, that's exactly true. Pardon?
It sounds like we're talking about a filter, or we're getting in that territory.
Exactly. We are talking about filter. So very similar considerations that, you know, like the one we just had here collectively lead us to demand that U be not just a filter actually, but an ultrafilter. And here's the definition of ultrafilter. So a family of sets is called an ultrafilter, first of all, if it's closed under intersection. If it's closed under taking superset, that's filter. So far we've said filter. And now what does ultra mean? Ultra means,
No
that
extension.
slide died. Oh, what happened here? What is wrong with my slide? Sorry about this. Somehow my Acrobat reader did just freeze. Now it goes again, but not really well. What is going on?
Probably because you're on Acrobat. Acrobat is really annoying on my computer too.
Yeah, okay. Yeah, the thing is that I only just got this laptop and I don't have a lot of experience with what works and what doesn't. So this is my second talk that I gave, and the first talk, it worked better. Okay, so, all right, so here is the ultra part. The ultra part says that every set or its complement must be in U. So whatever set you give to U, U is going to make a decision, true or false, right? Yeah, and that's, I mean, I'm not going to go into the details, but you really need that. You need that for trichotomy. You need this in order for this to you know, to give you a sensible notion of truth in your ultra product. And now it stopped working again. Okay. Oh, that is so annoying. Maybe I should just close down and take a different program. Oh, okay. I'm sorry. I'm going to stop the screen share for a second.
Yep, no worries. Take your time.
And
These kind of glitches happen.
Open it with preview. And I would like single page. And now I'm going to reshare the screen. Okay, that was the wrong. How do you go to full screen here? Enter full screen. Okay. Can you see it?
That looks
Yeah,
pretty good and is
that-
running super fast now.
And it's much better because now I can use the cursors as well. All right, so ultrafilter, and here is what was missing on the slide earlier. We actually also want this to be a non-trivial ultrafilter. That is, we want it to contain all cofinite sets. Cofinite sets are sets which are complements of finite sets. Okay, it's a bit roundabout. This is an ultrafilter. I also could have said we want all the finite sets to not be in the ultrafilter. Doesn't really make it any better. So we call it a non-trivial ultrafilter. It's one containing all cofinite sets, and such a filter exists by the axiom of choice. So, you know, we don't really get to choose U. U is somehow comes about very inconstructively, and that's one of the criticisms that people have with non-standard analysis, but I'm a set theorist, so I really don't care. I use the axiom of choice a lot in my daily practice, and actually so do all these mathematicians who complain about this kind of stuff. I mean, because, you know, life without the axiom of choice is really not so great. But in any case, so why is it called an non-trivial ultrafilter? Well, it's not hard to see that if an ultrafilter contains a finite set, then actually the ultrafilter is just all the subsets of n which contain a single natural number. And in that sense, it's just trivial, right? So as soon as you have an ultrafilter which does not have this property that it contains all the cofinite sets, it's really not an interesting ultrafilter, and your notion of truth will just tell you what's true about one coordinate in your sequences. So that's why we just call it a non-trivial ultrafilter, and that's, you know, and you will see how this is used, hopefully, if I stay within time limits. All right, so now we've got our non-trivial ultrafilter, and now we can define the ultra product. It's just the ordinary product, and you take the quotient by u, and by the quotient by u, what I really mean is you take the quotient of the product by this equivalence relation that I mentioned earlier, where you identify two things, two sequences, if they agree on a set which is in U. Or we also say if they agree in a U large set. Or we also say if they agree for U almost all n, right? So as I said on the previous slide, the point is you identify two things if the coordinates where they agree on are in U, or if the set, their truth value, the truth value of the statement R equals R prime is this set of coordinates, and if this truth value gets mapped to the truth value 1, right? Okay, so this is what the ultrafilter is. That's it, we've got our hyperreals. Okay, but we don't really have the hyperreals, we just have a set, right? The hyperreals are a field, so I have to tell you what the operations on this field are. Oh, but okay, first off, I want to say square brackets is the notation I use for the equivalence classes, right? So the elements of the hyperreals, the elements of this ultra power, this is also going to be what is called R star. R star is R to the n modulo u. So the elements of R star are equivalence classes of sequences, and we denote them like the square brackets of a sequence. All right, and here are the field operations and the ordering too. It's just defined component-wise, and then of course you have to take the equivalence class, right? So it's exactly the operations that I gave you earlier, except that you have to take the quotient. And of course you would have to check that this is well defined, right? That this that taking the quotient actually respects these operations, right? So you want that if you replace R bar and R bar prime by two different representatives of the same equivalence class, then the value of the product defined in this way doesn't change. And it doesn't. And the proof just uses that U is a filter, I guess. Maybe that it's an ultrafilter. But those are good exercises for you to check if you want to check these things. And also that you will have trichotomy. That's also just, it's very easy to check. That very heavily uses ultra, right? Because if you just look at two things, then the set of either as the set as it's described here of n where R bar is less than R bar prime, either this set of n is in U, or its complement has to be in U, and the complement is the one where R bar n is bigger or equal to R bar prime. And once you have that, you can again separate this set into two parts. The part where they're actually equal, and the part where one is strictly less than the other. And if the union of two sets is in U, you can easily check that one of the two sets has to be in U. That just follows from being ultra and being a filter and all of these other things. So yeah, so one of the three sets will have to be in U, where by three sets I mean the one where the strict less than relation holds, the equal relation, or the strict bigger than relation holds, and that's how you prove dichotomy. Does that make sense? A little bit?
Yep.
Cool. Okay, and in fact, we can do something very similar as we did to plus and times for any function from R to R. And for any relation as well, we can do something very similar as we did with the less than here. Namely, we can define their star extensions. So these, remember, actually, these are also the star extensions of plus and less than. But remember that I said I would never write the star on these operations because it gets tedious. So here, maybe I should have written the star to remind you. Okay, but for any function and relation, we can define their star extensions in just the same way. So if you think about it a little bit, this is exactly what we did on the previous slide. So the equivalence class of R is related, star related to the equivalence class of R prime, if and only if this set here is in the ultra filter. And the set is just the set of n where the relation holds for each n, for this n. And okay, so the thing with the function is maybe a little harder to parse, but if you think about it a little bit, this is exactly what we did with the plus as well. And let me just mention that actually, you know, functions, you can think of functions as binary relation, where for every x there exists exactly one y which is related to it. And if you do that, then you can also use the second line here to define what you mean by the star of a function, right? You just take the relation that represents the function and you take its star, and that too will agree exactly with what's written in the first line. So this just has to be the right definition of extending a function. And it is, and in fact, and I only mentioned this very quickly, in fact, even for higher typed functions and relations. So for example, for a relation, a binary relation between sets of reals, or for a function which assigns a set of reals to a set of reals, and you can go up in the type hierarchy, if you know what that is. Or if not, you know, you can take relations on the power set of the power set of R. It doesn't matter much. Let me just say, for these more complex objects, you can also define their star. And I won't go into that, but this eventually leads to the notion of an elementary embedding of what's called superstructures. Those are, you know, the whole type hierarchy built up over R, functions from R to R, functions from R to functions to R, whatever you want. And this star map will be very, very structure preserving. It will preserve a lot of structure. We already saw that it preserves the field operations. Well, we haven't quite seen that yet, but I will show you that in a moment. In some sense, it will preserve the field operations, but it will actually preserve formulas expressible in what's called higher order logic. And I'll try to give you a small hint of that, but you know, don't worry if you didn't understand what I said. Now it's only supposed to be a kind of sneak preview. So as a tiny first step down the road, let's define the star map. The star map goes from the reals into the hyperreals. And the star of a real is just the equivalence class of the constant function, which always takes the value R for every natural number. It's a sequence, the constant sequence with value R. You take its quotient by the ultrafilter. That's your star R. And we will, in time, identify this with the real R because it behaves exactly like the real R, which is very intuitive. I mean, even in the product, it behaves like R, right? Okay, so in fact, the star map is a homomorphism of ordered fields. I won't prove that, but it's really easy. It's a good exercise. And for this reason, we will identify R and star R from now, so that R becomes a subfield of typo star R, right? So the star map is a homomorphism from R to star R, but we're actually going to identify R to its image under star R. And I will stop writing stars on Reels as well. I'm already over time. Oh my God. I have so many more slides. I'm sorry about that.
That's super duper okay. I think we got a really solid introduction to ultra filters and ultra product. This
Yeah.
is super duper cool. We are, however, 7 minutes over time.
Yeah,
But-
I'm really sorry. So this
Hey, no
would have
worries,
been-
no worries, no worries, fine.
It would have been a great slide to end. You can read it now while we have the closing ceremony.
Yeah, so what we're going to do is I'm going to put a link in the chat for people to please give some feedback. David, feel free to take a bit of a bio break if you want to grab a glass of water or stretch a little bit. I think Lyndon's got a great suggestion of continuing this with the Bayesian analysis stuff. So please take 2 minutes, fill out the survey in the chat, and then we'll proceed with questions after that. So take a moment, fill out that survey about how this talk's going for you.
I think UTSC is the University of Toronto Scarborough.
Yeah, this math is super duper nice. Every time ultra powers and ultra filters show up, it's like very magical. Before we get into questions, I'm going to pause the recording.